A burning question about quantum computing is, for which interesting problems can quantum computers show an exponential advantage over classical computers? Factoring is, of course, a very prominent example, but there aren't so many others. One common thing to hear is that we should look to inherently quantum problems, let's say problems in quantum chemistry. So, do we have any such examples? In this video, I want to tell you about a fundamental problem in quantum chemistry, and tell you how we can solve it efficiently with a quantum computer, and also that we, or at least Matt and I, do not know how to solve it efficiently with a classical computer. I'll start with what is sometimes considered the most basic problem of importance in quantum chemistry, that of electron structure. Let's say we're modeling a molecule with some electrons that can be in n different spin orbitals. There may be some energy cost, C sub ij, for an electron hopping from orbital I to orbital j. But things don't get very interesting until you model interactions between two electrons. So we also assume that there's an energy cost, Ci/jkl, for two electrons at orbitals I and j scattering and ending up at k and l. Okay, just to keep it simple, I'm going to eliminate worrying about the one electron costs, as these are not too hard to handle. So given these costs, the task is to estimate the ground state energy of the system. Let me give the mathematical upshot of this problem. We're given as input a degree 4 homogeneous polynomial h with real coefficients c, I, j, k, l, the indices range from 1 to n, and quote-unquote variables, chi1 through chi-n, that are certain fixed matrices of dimension 2 to the n over 2. I really want to emphasize that these are completely fixed matrices. They're sometimes called Majorana fermion operators or gamma matrices. And the only input to the problem is the coefficient c. I could write down an explicit formula for the chi matrices, but instead I'll just now tell you everything you need to know about them. Okay, so here are the key properties of the chi matrices. First, these are symmetric matrices. Well, actually they're complex matrices, so I should say that they're Hermitian matrices. That is, the conjugate transpose of chi j equals chi j for every j. One thing this implies is that they all have real eigenvalues. Second, they square to the identity matrix, and this funny symbol 1 is my way of writing the identity matrix. So in particular, this means that all of their eigenvalues are either +1 or -1. So they sort of behave like Boolean variables. Third, and this is the most important, these matrices anti-commute. So chi j times chi k equals negative chi k times chi j. And this is all you need to know about the matrices. There's a certain sense in which these three properties here characterize everything there is to know about these 2 to the n over 2 by 2 to the n over 2 matrices. Indeed, it's not too hard to show that if the chi j's are any matrices satisfying these three properties, then the set of eigenvalues of h is unchanged. Okay, it just so happens that the 2 to the n over 2 is the smallest dimension in which you can find these matrices. Since we're here, let me mention one more property of these matrices, which is a fun, tiny exercise. It's that trace of chi j is 0, and more generally, the trace of any product of one or more distinct chi j's is also 0. Okay, now let's do one more little exercise just to get used to these properties. If we look at one of the general, quote-unquote monomials in H, chi I, chi j, chi k, chi l, and we take its conjugate transpose, well, that gives the conjugate transpose of all the chi's, but in the reverse order. And now by property 1, we can delete all of those conjugate transpose signs. And then we can start reordering the chi's using the anti-commutation rule. So we switch chi k and chi l at the beginning, picking up a minus sign. And now we can move chi l further towards the end, switching it with chi j and getting another minus sign, etc. And if we do this, I think 4 more times, we end up with the matrices rearranged as chi I, chi j, chi k, chi l again. So what we've shown is that this monomial is also self-adjoint. It's also a Hermitian matrix. It's equal to its conjugate transpose. And therefore, that in turn is true of H itself because the coefficients C are all real. And this means that the matrix A we're studying is Hermitian and therefore has only real eigenvalues. And this is a good thing because, remember, we're trying to estimate its maximum eigenvalue. Okay, so to summarize, we'll be looking at the degree 4 version of the fermionic or anti-commuting optimization problem. And as I said, you can either think of the chi j's as specific matrices of dimension 2 to the n over 2, or you can think of maximizing over any matrices that, square to the identity and anti-commute. And when you present it this way, it may look rather familiar. If you replace anti-commuting with just commuting, then in this formulation, it becomes identical to optimizing usual degree 4 polynomials over the Boolean cube over plus or minus 1 assignments, or equivalently, the weighted 4XOR problem. In fact, you can simulate the usual commutative version of the problem using the anti-commutative version. So if you look at a pair of chi's, like chi j prime, this degree 2 monomial squares to -1. So if you stick the scalar I, like the square root of -1, in front, it squares to 1. And moreover, it's easy to check that two terms like this commute. Okay, and from this, it follows that you can simulate n commuting Boolean variables by 2 times n anti-commuting ones. And hence, degree k Boolean optimization reduces to degree 2k fermionic optimization. For example, the degree 4 fermionic problem we're interested in is at least as hard as degree 2 Boolean optimization, which includes max cut, for example, as a special case. So this proves that our degree 4 anti-commutative problem is NP hard. In fact, a similar argument can be used to show that the task is QMA hard. Now, this is only for exact or near exact optimization, and we actually know that max cut is not actually that hard from the purposes of optimization. It has quite good approximation algorithms using semi-definite programming. So some of the results in our work are about the extent to which these approximations extend to degree 4 fermionic optimization. But our main interest in the work is not the worst case version of the problem. Instead, we focus mainly on the average case version of the problem, the most natural one where the coefficients are chosen to be independent Gaussian random variables. As a minor note, we're going to choose the normalization of these so that the sum of the squares of the coefficients is 1 in expectation. Now, this distribution on coefficients gives a random matrix model known as the SYK model. So Sachev and Ye are condensed matter physicists, and Kitaev is the quantum computing pioneer that you all know. This model has actually been studied in nuclear physics since the late 60s, but it took on a new life in the last decade when it was connected to the ADS CFT correspondence and proposed as a model of black holes. So here's a clip of Kitaev speaking about SYK and the connection between it and black holes. So the nice thing is, if you work on random degree 4 optimization with anti-commuting variables, you can also, as Kitaev says, say that you work on black holes. Okay, so what is known about the degree 4 SYK problem? Okay, so first of all, theoretical physicists, quote unquote, know that the maximum eigenvalue is order of square root n with high probability. Indeed, they've had this idea for like over 50 years. This figure from a 1970 paper is illustrating that although H is some kind of random matrix, its eigenvalue distribution does not seem to follow the Wigner semicircle law, which is depicted in the diagram here. Instead, it follows something that looks more like a Gaussian distribution, also depicted in the diagram. Now, since H has dimension 2 to the n over 2 and it has 2 to the n over 2 eigenvalues, if it really were Gaussian, we would expect the maximum eigenvalue to be around the square root of the log of 2 to the n over 2, in other words, order square root n. Now, actually, in the last 10 years, physicists have refined their prediction and don't believe the eigenvalue distribution is exactly Gaussian, but it's a reasonable first approximation. Now, unfortunately, not much of the very refined physics prediction has been rigorously proven. In 2019, Feng, Tian, and Wei verified the upper bound, that the maximum eigenvalue of H is at most order square root n with high probability. As for the lower bound, they didn't explicitly state any result, but you can infer from their paper that opt is not constant, like it's little omega of 1 with high probability. Now, this upper bound can be proven using a matrix Chernoff bound. That's not actually how the authors did it. They did something simpler, actually, but matrix Chernoff bound works. Now, this upper bound tells you that before you draw the coefficient C at random, you know it's very likely the resulting H will have max eigenvalue at most square root n. However, consider the situation where you do draw them at random, and now you want to certify that this particular H you have indeed has maximum eigenvalue at most square root n. It's not obvious how to do this, and if you studied random polynomial optimization before, you know that these Chernoff type bounds, these kinds of arguments don't yield any obvious ex post facto certificates. Okay, so now I can state the two main results in the paper. First, we give an efficient classical algorithm, specifically the degree 6 sum of squares algorithm, that with high probability certifies that a random instance of degree 4 SYK has optimum at most big O of square root n. Second, we give an efficient quantum algorithm that with high probability certifies that a random instance has optimum at least order square root n. Now, a few words about this second item. First, forgetting all about algorithms, this is the first rigorous mathematical proof that the optimum value of SYK instances is indeed as large as order square root n with high probability. Now, second, for optimization problems, you might not be used to looking for special certification algorithms that the optimum is large. In classical problems, you usually do this just by finding and exhibiting a good solution. But here, what we're trying to establish is that the maximum eigenvalue of an exponentially large matrix is large. So it's not even of an obviously NP flavor because the natural certificate is exponential in size. Finally, as mentioned at the start of this video, we don't currently know any classical algorithm that can efficiently certify op being at least square root n with high probability. Okay, so now I'll tell you about the upper bound and the lower bound. So let's start with the upper bound. So we're given as input a random degree 4 polynomial h, and we're going to collect its monomials into n groups depending on the index of the first chi. So I write it here as the sum. I write it here as the sum over, as I goes from 1 to n, of chi I times tau I, where tau I is like basically the sum over jkl of ci jkl times chi I chi j, chi j chi a chi k chi l. And actually I'm being a little sloppy here because in tau I you should really only sum over j, k, and l that exceed I, but let me just be a little bit sloppy with the indices in this talk. Okay, so let's also stick a 1 over square root n in front of the sum over I in h, and then stick square root n back into each tau I term. I only do this normalization rejiggering so that the tau i's become normalized with the L2 norm of their coefficients 1 in expectation. And then in this way, you see that actually each tau I pretty much looks like an independent draw from degree 3 SYK. Okay, so now the argument kind of begins. We can apply matrix Cauchy-Schwarz to this summation h to conclude that the opt squared, which is lambda max of h squared, is at most 1 over n, that's the square of 1 over root n, times lambda max of the sum of the chi I squareds times lambda max of the sum of the tau I squareds. Now the chi I squareds are just the identity, 1. So this first factor after the 1 over n is just n, and that cancels with the 1 over n. So really all that's left is this last expression, opt of sum of squares of the tau i's. Now the tau i's are of degree 3, so if we square them, we get degree 6. But a slight miracle happens when you expand everything out and collect terms using the anti-commutation rule as much as possible. The degree 6 part of sum of tau I squared actually cancels out. Now, it's not really a miracle. There's a good reason for this, and it's not hard to predict or infer that this is going to happen once you've played around with this anti-commutation stuff for a bit. But let me just leave it at that and just say that this sum of squares of tau i's is some degree 4 polynomial in the chi i's. And moreover, you can do a bit of calculation and express it like this, some constant b0 plus this degree 4 part with coefficients bi, j, k, l. And you can show that in expectation, the sum of the squares of these bi, j, k, l's is order 1, constant. Okay, so we've cleaned this up a bit. And now you see, if we want to show that the optimum of h is at most order root n, so we want to show that the optimum of h squared is at most order n, it suffices to show that this sum of squares of tau i's has optimum at most order n. And in fact, what we do is show the following theorem. For any worst case degree 4 polynomial at all, p, whose coefficients have L2 norm order 1, sum of squares of coefficients order 1, its optimum is at most order n. Okay, in fact, we even have this slightly more precise result that you see on the screen here. And this is far from obvious because do remember that there are n to the 4th monomials here. And so by our normalization condition, each one might have a coefficient of order 1 over n squared. And so the sum of the absolute values of the coefficients could be as large as n squared. And this is the most naive upper bound on the opt that you could have for a worst case polynomial. But we do manage to prove this theorem. And actually, very interestingly, the proof involves determining the Lovász theta function of a certain Kneser type graph. And there are actually some associated open combinatorics problems to do with this proof. They're quite interesting, but I'll leave it at that. Finally, let me just end this section about the upper bound by pointing out that the two inequalities we use in the proof, the Cauchy-Schwarz and the Lovász theta bound, which is a kind of STP inequality, these are both exactly the sort of things that have low degree sum of squares proofs. So if you know what this is, you won't be surprised to learn that you can carry out this certification in low degree SOS. And this is the reason why we have efficiently findable classical certificates that for SYK, the optimum is order root n. Okay, so let's move on to the lower bound. Here we want to certify that the maximum eigenvalue of H is at least order root n. Now, ignoring complexity concerns for a moment, one way to certify that a matrix, especially a very large matrix, has eigenvalue at least square root n is to exhibit a unit length vector whose quadratic form under H is at least that large. Or a convex generalization of this idea is to look for a so-called state matrix, rho, such that the trace of rho times H is at least square root n. So here a matrix is said to be a state if it's a positive semi-definite and of trace 1. So an example of such a state is just the outer product of a unit vector with itself. By the way, whenever I say trace here, for convenience, I mean normalized trace, the one where you divide by the dimension. Okay, so this is how we can find certificates for largeness of the eigenvalues of H by finding these state matrices. Now, one way to express a state matrix is actually as a polynomial in the chi matrices. In fact, one can show that products of the chi's form a linear basis for all matrices, and so this method is actually complete, if you will. So say we write some rho like this as A0 times the identity matrix plus A1 times chi1 plus A2 times chi2 plus etc. I mentioned much earlier that all chi matrices and products thereof have trace 0. So the normalized trace of such a rho is simply the constant coefficient A0. Moreover, we know that a matrix is PSD if and only if it's a square. Well, more precisely, a Hermitian square, like Q transpose Q, Q conjugate transpose Q for some Q. So with this formulation, we've actually expressed the optimization task in a way that refers only to the chi's somewhat symbolically, without actually needing to know what matrices they are, just their, anti-commutation and squaring to the identity properties. Okay, the difficulty, though, is that a generic polynomial expression for rho can have as many as 2 to the n terms. So it's not so obvious how to optimize over all rows. Just to get the flavor for this, let me describe for you an example of an explicit state, which I'll call rho 0. And this rho 0 is basically just a product of a bunch of these expressions, identity minus I times chi j chi k, like chi1, chi2, and chi3, chi4. Don't worry too much about the scalar I in there. It's just to make sure that the expression is self-adjoint, Hermitian. And also, note for the convenience, I assume we have 2 times n variables chi, just so that we'll have n factors in this example state, rho 0. Okay, so why is this a state? Well, first we check its trace. If you imagine expanding this like long product out, then the constant term will indeed be 1, so the trace is 1 as desired. Second, why is it a perfect square? Well, it's not completely obvious, but it's not hard to check either. First of all, these factors in rho naught commute with each other, so that helps. And in fact, it turns out that rho naught is almost its own square. That's in fact literally true up to the constant factor to the n. You just have to check, as I said, that these factors commute and that each one of these factors itself squares to basically itself. In fact, itself times 2. Okay, so together these show that rho 0 is indeed a state. Now, let's suppose hypothetically that the H that we were interested in optimizing was this one. Now, that's not a degree 4, it's just degree 2, but I'm trying to give like a simple example here. And again, don't worry too much about the scalar I that I stuck out in front. Okay, well, our state rho naught here actually certifies that this H has a rather large eigenvalue. To see this, we just need to compute the trace of rho naught times H. And we do this just by, multiplying rho naught and H together sort of as polynomials in the chi's and expanding everything out and using anti-commutation and squaring to identity and so forth and so on, and determining the constant coefficient at the end. That's the trace. It's not hard to check that this is basically like the dot product between the coefficients of H and the expanded out version of rho naught. And so we get 1 over root n from out front, and then we get 1 plus 1 n times. So overall, this gives square root n. So this rho naught here witnesses that the optimum for this simple degree 2h is at least square root n. Because we're able to rather explicitly write down this rho naught and compute its trace with h. And incidentally, by the way, this lower bound happens to be tight for this particular h. Its optimum really is equal to square root n. Just before we go on, let me just restate this with slightly different notation. I've got the exact same stuff as on the previous screen. We still have 2 to the n variables, but I'm just going to call n of them chi and n of them sigma. So you see I've like matched up like chi j and sigma j everywhere. It's nothing different. I'm just changing the names of half of the 2n variables for future use. Okay, so now we get to the interesting part. We get back to our goal. We have this random degree 4 SYK instance H, and we want to certify that its optimum is at least square root n. Okay, so as in the upper bound argument, actually, we start by expressing H as the sum over I of chi I tau I, where tau I is the degree 3 part of H that depends on chi I. So each tau I is basically distributed like a random degree 3 SYK instance. Okay, now it turns out that heuristically, these tau i's behave quite similarly to the chi i's. They typically almost square to the identity, and they almost anti-commute with each other and with the chi's. In fact, suppose we just pretend that the tau i's are equal to some newly introduced sigma i's that exactly square to the identity and anti-commute with themselves exactly and with the chi i's, like on the previous screen. Well, then if you look up at H, it would be exactly as on the previous slide. If the tau i's magically equal these pristine anti-commuting sigma i's, it would just be, sum of chi I sigma I times 1 over root n. And we could write down our old state rho naught from the previous slide, and this would certify that opt is at least square root n, exactly as desired. Okay, so the problem is the tau j's are not exactly equal to these newly introduced sigma j's. But the trick or the idea in this lower bound argument of ours will be to somehow rotate rho 0 in the direction that takes the sigma j's to the tau j's. So what does this actually mean? It means we're going to define rho sub t to be rho 0 conjugated by a unitary ut, where ut evolves the sigmas towards the taus for some amount of time t, and t is going to be a small constant parameter we'll choose later. Okay, and this idea is known in the physics literature as a variational argument. Okay, so that's the rho t we're going to try to use. You do some calculations involving the Baker-Campbell-Hausdorff formula, and you find that trace of rho t times h, which is what we're trying to lower bound, is at least t times square root n minus t squared times the maximum eigenvalue of a certain error polynomial. And this error polynomial is an explicit degree 12 polynomial whose coefficients are degree 3 monomials in the original coefficients CIJKL of h. And what we now want to do is prove that the maximum eigenvalue of this error polynomial is at most something like 100 square root n. Now, if we can do this, then looking at our formula, we see that by taking t suitably small, like 0.001 or something, we get, as a consequence, that opt h is at least omega, big omega of square root n, as desired. And okay, Matt and I were able to prove this fact about the error polynomial by some kind of matrix Chernoff bound type argument. So on one hand, that's great. It indeed shows that rho t is with high probability a certificate that opt of h is at least order square root n. On the other hand, as I mentioned earlier, these Chernoff type arguments seem to only work before the fact. After you've chosen the coefficient CIJKL of h, this defines an error polynomial, and although it's very likely to have maximum eigenvalue bounded by 100 times square root n, we don't know how to certify this efficiently. So, just to summarize, given a random instance h of the degree 4 SYK model, we can immediately write down a state, rho t, which should be a witness that the optimum of h is at least order root n. Unfortunately, we don't know any efficient classical algorithm that will certify this with high probability. But it's actually easy for a quantum computer to certify this with high probability. It just has to literally prepare the state rho t and check that its trace value with h is large enough. And remember that this is all happening in dimension 2 to the n over 2, and this means that rho t just consists of n over 2 qubits, and it's easy to do this verification in polynomial time on a quantum computer. Okay, so in conclusion, we studied the SYK model, which is the natural average case version of a fundamental problem in quantum chemistry. We saw that there's an efficient classical algorithm for certifying its value is at most order square root n with high probability. And we saw that there's an efficient quantum algorithm for certifying its value is at least order square root n with high probability. And we don't know any efficient classical algorithm for the latter task. So please, if you can find one, do that, or else find evidence that no such classical algorithm exists.